Welcome back, everybody. This is my third video in my attempt to build a neural network using the C programming language. Before we get into new material, I just want to take 5 minutes or so to review what we've done in the previous video. In our previous video, we used a very simple neural network framework. It's called batch gradient descent. And what we did was we used bigrams, very simple bigrams, one character input, one character output. And we encoded those bigrams in using one hot encoding. And so we got our inputs are one hot encoded, and our targets are one hot encoded as well. We also produced a weights table, which was 27 by 27 because our alphabet is 27. And this was random initially, so it's randomized. We then used this formula to produce our expected output, our Y predicted, by multiplying our weights, which are 27 by 27. We're multiplying those by X, which is our inputs. And our input was huge because we had, we only have like one gigantic batch of data, 228,000 bigrams, each one hot encoded. So each bigram is 27 binary digits, zeros and ones, basically. We also used a loss formula here to produce a loss. This is just a straightforward mean squared error loss. We also used a function called softmax, which I introduced you in the last video, to get the probabilities. And we used a little bit of calculus to do backpropagation. And the purpose of our backpropagation was to calculate the loss with respect to our weights. We wanted to know how, what kind of change in W will affect our loss. So we want to make small tweaks to W to push our loss in a good direction. And the way we calculated this was we used the chain rule. And once we calculated the gradient, then we could update our weights. We're using the gradient of the weights. And we also used the learning rate to do the update. And again, I think I mentioned that the learning rate is basically just a floating point number that tells us how fast or how slow our iteration is taking place. In other words, how fast or how slow we're getting to a good loss. So we basically repeat these steps here. All these steps are repeated a couple 100,000 times or something, I'm not sure. And we end up with optimized weights. Once we have the optimized weights, we can convert them into probabilities, and we can use those probabilities to, we can sample those probabilities to produce some new names. And we've done all that in the previous video. So, actually I can probably show you just quickly, just a little bit quickly. I can show you the C program we did last time. Was right here. And here's our loop to do the try to minimize the loss. You can see the first thing we do in our loop here is we multiply the encoded inputs times the weights to get the log counts or the log digits. And then we get the probabilities by using the softmax function. And we can print out the loss here by using this getLoss function. And then we calculate the gradients here. This is our first gradients we get. And those are the gradients of the weights array. And then we update the weights array. And we just do this for loop 150 times, or could have done it a lot more than that, but anyway. And once we optimize the weights and we minimize our loss, we can then go and call this function here MakeMore to give us 20 more names. And we can also get this is the Python program that produced, and by the way, the Python program and the C program produced exactly the same outputs. So I kind of know everything's working, but you can see what it does is first it encodes the input using one hot, computes the log counts just by multiplying the input by the weights. It computes the probabilities by first getting the counts. How does it get the counts? It just exponentiates all of the log counts. It then produces the loss by getting the negative log or negative loss log of the kind of the average of all of the bigrams. And in the Python program, the backward pass is very trivial. You just do one line. And this does all the calculations of all the gradients. It does all the calculus you need. Everything is done in that one line. And then, of course, you can update. After that is done, you can then update your W data by taking your W data and you multiply the learning rate times the gradient. And you just subtract that or add that to the W data. Then you get a brand new version of W. And you do that 150 times, then you go in here and you can make some more. You can make 20 more new names. All right, I think that's enough for this. Let's move on to new stuff here. Let's close this. So I want to go and start talking about this is my third video, but it's really the second video of MakeMore that was made by Andrej. So some of the concepts we're going to introduce, well, we already know about softmax, but we're going to introduce a hidden layer of neurons. We're going to introduce bias vectors. We're going to introduce an activation function. We are going to introduce an embedding table. And we're also going to change our bigrams to have a block size of 3. I'll talk about that in a bit. And we're going to introduce dimensions, which are part of the embedding table or the lookup table. I think I didn't put the lookup table here. All right, well, let me add that in. Because we also have here, for example, a lookup table. The lookup table is actually table C, and the embedding table, I call the embedding table EMB, embedding table. And we're also going to introduce the idea of a mini batch. In other words, the last video was using batch gradient descent. We had one gigantic batch, and we did gradient descent on that one batch. Now we're going to be using a mini batch, and usually our size is going to be maybe 32. And what that means is that from the entire batch, we will randomly select 32 rows of input, and we will process those, and then we'll choose another 32 and process those, and another 32 and process those, and that's a lot more efficient than having just one gigantic batch. The batch we had in the previous video was 228,000 rows by 27 columns, and so 228,000 rows it's not really very much when you're dealing with large neural networks. So if we had rows of a million or a billion, then obviously multiplying these large batches would be very difficult, and probably wouldn't even have the memory to do it. So that's why we break up the large batch into mini batches. We'll also talk a little bit about cross entropy, which is the way we work out our loss. We don't just use mean squared error. We use logs to work out the loss. Okay, so I think we'll start by looking at our bigrams. That's where we usually start. So let me close this and start with our bigrams. Where do I have that here? Well, you know, we started before. We had a bigram like, well, we had our word was Emma. I think it started off with Emma followed by Olivia, and so on. And we broke this up into bigrams like this. We had dot E. That was our first bigram, and then our next one was EM, and our next one after that was MM, and then MA, and then A dot, and so on. So we basically had one character on one side. We had the inputs and the outputs. So this first column here would be the inputs, and the next column would be the expected outputs. But what we're going to do now is we're going to change these bigrams. We're going to be using 3 characters for the input. So the way our bigram is going to look now, it's going to look like this. For example, it'll look like, let's say dot dot E, or let's say just dot dot dot. We could say that, and we're expecting an E, I guess you could say that. And then we have dot dot E, and then we end up with an M. We're expecting an M. Then we have dot EM, expecting an M, and then EMM, expecting an A, and then MMA, we expect a period, and then MA period, you're expecting like, I guess an O or something. Or we just start with another one, I guess. But you get the idea. The idea is that we're going to have 3 characters for our input. So this is going to be our X. This one here is going to be X. And this other line here, oops, is going to be Y, our outputs, or that. So our input, because we're using many batches, our input X is going to be 32 rows, which is our batch size, by 3. And our labels for our targets y will just be 32 by 1. So this y is our targets or our labels, and this x is our inputs. Okay. So that's what our new bigram model is going to look like. But we're also going to have what we call a lookup table. We're going to be using a lookup table here, and the lookup table will be consisting of the length of the alphabet, length of alpha, which is equal to 27 in our case, rows. So our lookup table will have 27 rows, one row for each character of our data, of our alphabet, and it will have the number of columns in our lookup table will be what's called the block size, or the dimensions. Dimension. In our case, our dimension is going to be equal to 2. We'll get to exactly what that means in a bit. So you can think of our lookup table as being, right now, it's 27 by 2. Okay. And by the way, this lookup table initially, this lookup table will be random floats. Random floats. Okay. And by the way, this by having 3 characters for our input, the terminology they use is block size. So if you look at our x here, you can say the 3 here is the block size. This 3 is the block size. BLOCKSIZE. Got to get all these words out into the open so we're all on the same page. So what that block size means is we're using 3 characters of input to predict the next character of output, basically. So some of the parameters we're using are, block size is 3. Our length of alpha is 27. Our dimension is 2. You can think of the dimension right now. You can just think of it as xy, as the xy plane. Why do I keep typing? PLANE. XY plane, and you can think of this table as each one of these 2 values in this table are an x and y value. That's, I guess, it's one way you can just think of it. Okay. So now what we have to do is we have to say, well, we also have this concept of an embedded table. Embedded table. And the embedded table is made from X here. It's made from X and C. The embedded table is made from X and C. So X is here. It's our 32 by 3 right here. That's our input table. And C, we said, is 27 by 2. Okay. So our lookup table is random, and our input table is one mini batch of input. So we're going to use those two tables, or those two matrices, to make up this embedded table that I just call it E for the embedded table. Now, to give you the big picture here, let me bring up a diagram I did here. Let's see. Where do I have it here? Right here. So here's a diagram, kind of a block diagram I made up, so we can see what we have. So let's just put some of these things on. This, the size of this X here is our input, which is going to be 3 by 32, which is our, this is our block size. And this is our batch size. Okay. And our lookup table is going to be 2, which is the dimensions, by the 27, which is our alphabet, or the length of our alphabet. So we have these two guys here. We have 1 and we have 2, and we have to combine those to make up 3, which is our so-called embedded table. And how do we do that? Well, first of all, let's take a look at this embedded table. The embedded table is going to be 32, but its width here, the number of columns, is going to be 3 times 2, which is equal 6, which is the block size times the dimensions. Okay, so that's going to be how many columns we have. 6. It's really 32 rows by 6. Okay, so let me show you how we first worked that out, because we do have our inputs, like, we do have this is given, the input is given, and our lookup table is given because it's a random table of random floats. So how do we do that? Okay, well, let's take a look. Let me see if I can bring up another one here. Embedded. I think this is it here. Okay, let's take a look at this one. So we have our lookup table, which is 27 by 2, 27 rows by 2, because 2 is the dimension. And we have X, which is our block size, which is the number of bigrams, which is going to be 32. Our batch size is 32. So we have C is just random stuff in there. Okay, there's 3 and 4, 1, 2, 5, 6. These are floating point numbers that we have in here. These are just random numbers that we started with. But our input is one mini batch taken from the entire batch. Okay, so for example, this 5 here could represent the letter E. 3 is a C, and 7 is C, E, G. I guess 7 is a G. So what we're going to do is, in order to build this embedded table, we're going to go through the input table one value at a time. We're just going to start with 5, then 3, then 7. Then we're going to go to the next one, and the next one, and the next one, next. We're going to just loop through the entire input table here, just one value at a time. And remember, these are integers here. Okay, so we grab the first 5, and that is an integer which points to the row of our lookup table down here. Okay, so what we do is we take this row here that has these 2 floating point numbers, and we stick them in to our embedded table. Remember, our embedded table is 6 by 32. I guess I could write that in here. This is like our batch size. Oops. Our batch size here is 32. Okay. And actually this is also 32. I can just take that out here and just stick in here that this is 32 as well. So one mini batch. This one here, 27, this is our alphabet size. So what we do is we take out, actually let me see if I can make this a little bit better here. I'd like to try to use some newer technology here. And see how this works. So I have a better pointer here. So we're going to go through this guy here, one integer at a time, through this whole input array. We take 5, we go to row 5. We take out that row. In our case, the dimension is 2, so our row just consists of 2 values. And remember, these are floating point values that are just random. And we stick them in here at the beginning of the embedded table. Then we go to the next number in our input here, which is a 3. And we go to row 3 here, which is the 3 and the 4. And we stick that in next into our embedded table. Then we go to 7. And we're down here on row 7. We take the 5 and the 6 and we put them in here. So, just for example, suppose I had here, well, I don't know. Let's say I had in the next guy here, if I had a 2, suppose I had a 2 in there. Well, then I would go to 0, 1, 2. I would go to here, and let's say I had, I don't know, a 4 and a 3. I would take that 4 and the 3, and I would put them in here. 4 and 3. Okay. So, and I would just continue going through the whole X here until I've done the very last guy way down here in this corner. And that would just fill this whole guy up. Because if you look at, actually this laser pointer is kind of silly. Let me cancel that out maybe. I like to try things, but sometimes they just don't look good. Let me go back to this one here. Like if you look at the size of this table here, this is 6, actually it's 32 by 6. I think that's 192. And if you look at this one here, is 2 by 27, is 27 by 2, which is equal to 4, is that 54? And this one is 32 by 3, which is equal to 96 times. We're going through this X input 96 times. And each one of these 96 iterations, we're pulling out 2 items from C. So 96 times 2 is equal to 192. And that's why we get our embedded table is 192, is because it works out that way. Okay, so let's put this thing aside here. We don't need that anymore. And okay, so now we have here, we have our embedded table, which we've managed to get. Oops. Let me get rid of that here. And now we're going to use that to generate our hidden neurons. So we're going to start with 100 neurons, like this. So you can think of each one of these guys as being a neuron here. And we're also going to have a weight table, which I don't show on here, but I'm going to have a weight table which is going to be how big? Let me just check that. Let me look at the code here. Our weight table is going to be the block size times dimensions, which is going to be 6 by our hidden nodes, which is going to be 100. So let me just put that aside here. So this guy is going to be 100, and then we have our weight here. Our weights are going to be 6 by 100. That's our W table. And again, it's initially, the W table is random. And by the way, this is W1, because we're going to have 2 weight tables. We're also introducing a bias as well, which I don't show either, but I'll put that here. This is B1, which is just going to be 1 by 100. Okay. And the way we work this out basically is to get the value of these neurons here, our formula is just going to be straightforward. We're just going to say, okay, we'll take H is equal to E. Well, let me just do it the proper way here. Because E is our embedded table, which is our input. We're going to take W1 times E plus B1. This is really the formula we're going to use to generate all of these numbers, all of these neurons. Okay. Now, once we generate all those neurons, we are then going to have to activate them by using the tan-H function. So I'll just write that in here. So this Z here is going to be tan-H of H. So if we take each one of these neurons in here and we activate them all with the tan-H function, then our numbers in here, after activation, they're all going to be basically from -1 to +1. They'll be between, because the hyperbolic function tan-H will just squeeze everything, all of these numbers that were just multiplied by this formula, it's going to squeeze them all into between -1 and +1. And then we have to go from our activations, we have to go and somehow generate our answers here. And the way we're going to do that is we're going to say YP is going to be equal to weight 2 times our activated neurons plus B2. So we're going to have W2 and B2, and W2 let's say W2 is going to be 100 by 27. I think that's what I have here. W2 is going to be 100 by 27, and we also have B2, which I think is just 1 by 27. Is that right? Yeah, okay. So, and then we use this formula. So here's the formulas we're using. We're using this formula here. Let me put that in red. This is the first formula we use, and then this one is the second formula we're going to use, number 2. Okay. So we're going to start off with random W1 and W2. We're going to start off with random B1 and B2, and we're going to start off with a random lookup table. All be randomized. And so our procedure is to basically, we're going to start by building up this table here, building up the input. And then once we have E created, we can then use this formula here to compute the H, the neuron, the value of the neurons, of the 100 neurons. Once we have the 100 neurons computed, we can then activate them using the tanh function here. And so now we have all of the neurons here are all activated. Once the neurons are all activated, then we can use the second formula to produce our outputs here, or our expected outputs. Once we know what our outputs are, then we can compute the loss. And once we know what the loss is, we can then use backpropagation to work backwards and try to get all of the gradients we need to make adjustments to all of our weights and biases, so that our loss will be better on the next iteration. All right. So let me just close this guy here. Excuse me. I have a messy picture that I made, but let's see if we can make some sense of it. Let me make it full screen here. Okay, so we started out with our lookup table. Now I don't have X here. Let me put X here. Let me just use the same color here. Oops. Okay, so here's our X. So X, we said, is going to be 32 by 3. Because remember, our bigrams now are 3 characters on the left side, 1 character on the right side. So X is 3 characters, and our batch size is 32. So we use this X together with C to produce E, and I've shown you how we do that. We ended up with a 32 by 6, which is our E, and that now is our that's our input. So the first thing we have to do is we have to multiply. We have to do this formula here. This is our first step here. Is we want to produce all of our hidden layer. This is our neurons in here. We want to make all of these values. So we multiplied W1. Remember, W1 is randomized. We multiply it by our embedded table, and we add B1, and B1 is also randomized. Okay. And so that gives us all these values in here, 100 values there. And then what we have to do is we have to activate those guys by using this formula. So this was our number 1, this is number 2, okay? And now we have all of our activations in here. And remember, these are like -1 to +1 because of the tanh function. Well, now that we have our activations, we want to produce our output, which is going to be our 27 neurons. So basically what we're going to do is we're going to use this formula here. YP is W2 times Z, which is the activations, plus B2. And again, W2 is random, B2 is random, and that's going to give us our output, 27 neurons, but it's a batch size, so it's basically going to be 32 by 27. Okay, so if we do that, let's take a look at some of our formulas here. Remember our loss here, very straightforward. Let me change back to red here. I keep thinking that eraser. So our loss is just going to be like that. So you can see that our I'm just doing it very generally. Our loss with respect to our predicted is just going to be YP minus Y, but it's basically going to be the sum of that divided by N, the number of bigrams we have. So we have DL DYP. So I'll just put that in green here. This we can figure this out just by subtracting our predicted values. We could subtract our actual values that we're trying for from our predicted values, summing them up and dividing by a number of 32. Well, so we have that, but the problem is that we need 5 more derivatives, and here they are. We need our loss with respect to our input table, or our lookup table rather. We need our loss with respect to weight 1 table. We need our loss with respect to B1 table. We need our loss with respect to W2 table. And we need our loss with respect to B2 table. So we have this guy here, number 1, but we need 5 more. We need these other 5 derivatives to work to basically we're going to have to update all of those tables to get another, to do the second pass. Okay, so to do the second pass, we'll need to work out those 5 derivatives. All right, so let's see how we do that. Let me adjust my chair here a bit. I'm trying to do this whole thing in one session, so it's pretty sloppy. It's not at all like the professional YouTubers do. Okay, so let's start by doing DL and the loss with respect to B2, which is the easiest one. And you can see to get this guy, we already have this one here, DL DYP, and we have to multiply it by DYP with respect to B2. But if you look at our formula, where was our formula? See, YP, here's the formula here. YP equals W2 times Z plus B2. So DYP dB2 is just 1. So that should be pretty easy to do, since this guy here is just going to be a 1. Okay, so now we have DL dB2. DL dB2, we have this one. I'll put an X through it. Now we have to work out DL dW2, this next one here. So how do we do that? Well, DL dW2 is just going to be DL, this is DL dyp times Z, our activated function. Because if you look at the formula here, this formula, if I say D, where am I here? This is my chain rule formula here. DL dB1, well, that's going too far. That's too far. Where am I doing this one here? D loss with dW2. Do I have that here somewhere? Yeah. Here it is right here. We have this one here already, but we have to work out dyp dW2. Well, dyp dW2 is equal to Z. See, dyp dW2 is just equal to Z. So that's why we get this guy here is just the dl dyp times Z, which is dyp dW2, just by this chain rule here. Okay, so now we have this one, d loss dW2. We have this one now. So we're working backwards. We did the easy one, B2, D loss with respect to B2, D loss with respect to W2, and now we have to go back to the loss with respect to B1. Well, that's even further. So if you look at the equation here for DL dB1 is, again by chain rule, DL dy predicted times dy predicted dz, which is W2, and this was just the sum of these y's, which we have. Dz dh, this next one here, is basically going to be, if you look at what z is equal to, like y is equal to tan h, so you could just say z equals tan h of x. So dy dx is equal to 1 minus tan squared x. So what am I saying? I'm saying the derivative of tan h is 1 minus tan squared. 1 minus tan squared. So that this guy here, right here, is basically 1 minus tan squared. Okay, and then the last one here, this one, dB 1 is just going to be a 1. Okay, so if you look at this chain rule, you see how these things cancel out. These cancel out here, this cancels out here, cancels out here, and you're left with the loss with respect to dB1. So now we have this one worked out. Let's see. Now we have this one worked out. So now what we need is the loss with respect to W1. Well, that's very similar. The loss with respect to W1 right here is just going to be just exactly what we had before on this chain rule, except that dH dW1 is going to be equal to E, the embedded layer. Okay, so now we have this one. So the last one we need is the loss with respect to our lookup table. Well, what we have to do is we have to get our loss with respect to our embedded table. And the loss with respect to our embedded table is like this. And you see it cancels out, cancels out, cancels out, and we get all the things we had before, plus we multiply by W1. And that gives us our loss with respect to our embedded table. But then what we need to do is we have to unembed E back into C to get our actual into C gradients. Okay, so we have to unembed E to get the gradients for C. We need to get delta loss with delta C. We have the loss with respect to E, but we have to get the loss with respect to C. And the way we do that is by unembedding the gradients from E into a C gradient table. Yeah, I know this is getting to be a nightmare, but if you go through slowly, step by step, I think it sort of starts to make sense. So let's see, how do we unembed the E table, the E gradients into C gradients? Well, let's take a look at that. How do we unembed that? Let's see, unembed is, I believe that's here. I have that here. Make that a little bit bigger. Okay, so there's our unembed. So with unembedding, again, we start with this 1 here, okay, which is 5. So we start right here. We start with the and remember, these are the E gradients. You can think of these are the E gradients. So these are floating point number E gradients. So we take the first 2 out here, and then we say, where do we put them in the C gradient table? We put them in row 5. We put them down here. So you can see what we did. This is the C gradient, and this is just our X input. So I think it would have been better if I labeled it. If I label it like this, this should be. Let's see. I think we do. Step 1. We take out the first 2 guys here. We take the 1 and the 2 out, and then we figure, where are we going to put them? Well, we take the 5 out here, and then we go to row 5 here, and that's where we stick these guys. So it's like number 1, and then this is like step number 2 here, and then step number 3. So what we're doing is we're now kind of going backwards. We're undoing, and we're producing here excuse me, the C gradients. So now we have them all. If you look, we have the W1, B1, W2, B2, and C. So we have 5 sets of gradients. 5 sets of gradients. All right. Let's move on to some code and see how this works. That's the interesting question. Where do we get some code here? Okay, let's first look at the Python code. Let's take a look at the Python code here. Okay, let's see if we can go through line by line here and see what it does. Well, we import Torch, we import Torch neural network as F. And now these lines here are my lines. These ones here are my lines. I've I need them in order to, again, I'm repeating myself, but I need these lines. In fact, this one as well. There's actually all of these lines. These first 3 lines here, I'm using them to create the weights and the biases and the C table. So basically, oh no, sorry, I got that wrong. I'm using, yeah, I gotta, these 4 lines of code here, I'm using for getting random batches. Because remember, we have thousands and thousands of bigrams, and we want to grab randomly 32 at a time. Our batch size we've set at 32. So I want to grab 32 bigrams at a time, and that's our batch size. And so I'm using the standard C library random function to do that. But for generating the random numbers for all the tables, I'm using the GNU scientific library. So to generate all of the random numbers I need for C, for W1, for B1, for W2 and B2, I'm using the GNU scientific library. Whereas the C random number library is only for getting the random batches. Okay, because they're just basically integers to grab 32 random lines of batches. I set these parameters here, print options full, so that I can see all of my answers instead of just partial answers. And I set my precision to 6, again, because I'm using floating point numbers. So the best precision I can get is about 6 decimal points. I think my voice is starting to go. I might have to do this in 2 videos. Anyway, okay, moving on. I also made this function here for generating all these random parameters for these 5 tables. Okay. That's nothing new. You've seen that I think in the previous video. Now we come to this function here. You notice the block size is 3, and we're going to generate X and Y here. Okay, and you can see we're doing for W in words. Okay, and we're just going to produce these X and Y tensors. So X is going to be 3. No, or the number of rows is going to be a number of bigrams, and number of columns is going to be the block size, which is 3, and Y is just going to be the number of bigrams by one column. Okay, so we go and we read in the names. We go through just what we did before. We create these 2 functions. Remember, string to integer, and integer to string. We also set our block size here to 3 and our dimensions to 2. And now here's something that I haven't talked about yet, but it's a good opportunity to talk about this. What we're going to do is we're going to take our words and we're going to split them into 3 pieces. We want to have a training set, and our training set is basically going to be 80% of our words. So for example, if we have 32,000 words, then our training set will be, let's say, the first 80% of the 32,000. And then that's the training set. X and Y are the training set. XDev and YDev are going to be the development set, and they are going to be 10% of the words. And then the testing set for X and Y will be the next 10% of the words. So if I just was to draw that out here, let me just show you. If I go here, so all we've done there is, if we said, if this is our total, like our words, we have 32K, then what we're doing is we're saying, okay, the first 80% are going to be X training. The next 10% here are going to be X for development. And the next 10% will be X for testing. Okay? So, and the reason we do that is because when we're training, we're going through this loop here with all of these words here in our training set. When we want to make new words, we're going to use, for example, our development set or our testing set to try to make new words. Okay, I think it'll become more clear once we get into the more of the code to do it. So let's take a look and see what we got. So we split here our X's and Y's. We split them into three chunks, and they all call this build data set. Build data set, which we saw up here. Build data set. Okay, how many words we want. All right, now we go through my function that I wrote here. I'm making B1 to be 100 random, just basically a vector. W1 is going to be block size by dimension, so it's going to be 3 by 2, which is 6 by 100. Now, what I'm also doing is I'm taking all of these random numbers, which are 6 times 100, which is 600, and I'm dividing each one of them by the square root of 6. So we're basically taking random numbers, but we're kind of tweaking them somehow as a function of block size and dimensions. So they're not really random. They kind of have some kind of, you could say there's some DNA in those random numbers that have to do with block size and dimensions. I don't know any other way to say it. And then when we make W2 is going to be 100 by 27, so 2,700. We're going to multiply those by 0.1. So we're going to scale them all down by a tenth. Again, these factors that were it seems like it doesn't make any sense just to take a random number and then just to divide it by something or multiply it by something. Like, what the heck good does that do? Well, again, this is kind of the art of building neural networks, just like the learning rate is kind of an art to get the learning rate correct. Getting random numbers to perform better is that's kind of also an art, at least in my opinion. But who am I to say? Amateur. B2 is just 1 by 27, and then here's our lookup table, which is 27 by 2. Our lookup table. So our parameters are going to be these 5 guys. We're going to have to find the gradients of all of those 5 tables. Okay. And we start with a learning rate of 0.1. And we're going to do a loop of 200,000 here. 200,000 times. So here's our program here. So a mini batch construct. So what we're going to do for J in range 32, we want to get 32 of these bigrams. So I'm using the lib-c to extract 32 random ones from the training set. And when I extract them, I put them in here. I create a tensor out of them. Because here I just had a list here, and I'm just appending these 32 guys into the list, and then I'm changing it into a tensor. Okay. So there I have my mini batch. Now this line here does the embedding. Now this is, don't ask me how on earth this works. This is so confusing, but it's if you watch Andrej's video, he'll talk about a feature called broadcasting, and somehow when you're dealing with arrays and indexing into arrays and viewing arrays in different ways, what I showed you with my C program, this one line will do the embedding. So it takes basically C, and it takes X, and it produces EMB, all in one line of code. And then what it does in one line here, it multiplies EMB by the weights and adds B1, and then does the activation 10H all in one shot. And then he produces the log counts by multiplying H by W2 and adding B2. And then he uses the cross entropy function to work out the loss. And remember, cross entropy, we're looking at the sum of the logs. We have to convert them to log counts. We have to convert them to using exponent and logs and averaging it all up. It comes out to kind of a mess, but I've done this in my C program, so make probably to you C programmers. In fact, I'm writing this for C programmers, so you people who already know Python are probably not getting that much out of this, but anyway, so and then we go into backward pass, and look at how beautiful the backward pass is. One line. That one line computes all of these gradients using those formulas I showed you a while back. That one line does it all. And then what we do is we just update everything. We update because P is those parameters, are those 5 gradients. C, W1, B1, W2, B2. It just updates them all. So there's our main loop here, that we're going to do this for 200,000 times. Okay. And after we do that 200,000 times, what we're going to do is we're going to examine the loss of our training set by just doing EMB is, instead of just doing here an embedded table that is only taking 32 bigrams, what we do down here is our embedding table is going to take the entire training set, which is thousands and thousands of bigrams. And then we compute H, just like we did before. We compute the log counts, we do cross entropy, and we can print the loss. And we can then do the same thing for our development. Remember, the development part of the data was 10% of the data, and we produced the loss of the development set. And we could also produce the loss here of the training set if we wanted to. But then we go into make more names, because we've already got all of those 5 parameters, C, W1, W2, B1, B2. All those 5 parameters have been optimized for a minimum loss. So what we can do in here is we can say, okay, let's start off with, this is going to be our word out. And we start off with basically an array here of 3 zeros. Block size is 3. And we embed that one bigram, we embed it into C to give us the embedded data. And then we compute H. We compute our log counts. We compute our probabilities. And now I switch over to my code here. All of this is my code I flatten the probabilities. I convert them to list, and then I call this multinomial function from the GNU scientific library. I pass it in the probability distribution, and I get an answer back here that is remember, this output, this n here is going to be an array of 26 zeros and 1 1. So this multinomial function will use this probability distribution to pluck out one random number, and all the rest will be zeros. And then he just adds that to the context and adds that number to the output, and he goes around again this while true loop until he hits a period. Once he hits a period, he basically prints out the word. And then he goes and gets the next, and then he does another loop here to print out the next word. This goes on and on. And if you look at my program, my C program, which is very similar, if I look at my main loop here of 200,000, I start my forward pass by getting a mini batch, and I'm getting it from the training set. I then do the embedding function. I then calculate H, which is embedding times W1. I add the bias onto H, so that's like W1 or E times W1 plus B, and then I activate H. Basically, this gives me like the Z array I was talking about, but I'm just using the same array. I get the log counts by multiplying H times W2 and adding in the bias 2, and then I call cross entropy to give me my loss, and I print the loss. So I make one pass here, just like we did in the Python program, and then I start back propagation. So I get the probabilities here. The first thing I do is I calculate dl dy. I get the B2 gradients. I get W2 gradients. I calculate dH dz because I'm going to need that. I transpose W2 because in order to do the multiplication of dl dyp with W2, I need to transpose it. That gives me dl dh, which is the loss with respect to h. And I also get dl dz. And you notice the multiplication, array multiplication functions I wrote. This one here, mult-ab, is standard array multiplication. But this axb function I wrote, this one just does element-wise matrix multiplication. So in other words, this one here just does A11 times B11, gives us C11. And A12 times B12 gives us C12, and so on. So it's just element by element. And then I get B1 gradients. I get W1 gradients. I transpose W1 so I can do the multiplication to get my E grads, my E gradients. And then I have to do, unembed the E gradients to get my C gradients. Wow, that's a lot of coding. Well, you can see I'm down at 677 lines. Then I update all my 5 parameters, W2, B2, W1, B1, and C. And then, of course, I have to make sure that I don't run out of RAM. I got to free everything up. And I can go back up now, and I can do loop number 2 or loop number 1. I start at 0, I go do the next one. And I can do this 200,000 times. And once I finish that, then I can do, here I have a function here just to print my final C, to print my final lookup table. Because remember, my lookup table is going to keep changing. It started out randomly, but my lookup table is going to keep changing little by little. So I print out my lookup table here, but then I do the, I want to do the loss here for the training data. I also want to do the loss for the development data. And I commented out the loss for the test data. And the only reason I did that is because Andrej doesn't do that in his Python code. And then we have MakeMore here function. So I make 20 more names. All right. So the first thing I want to do is I want to show you after one pass, after 200,000 passes, after going through this loop 200,000 times, what I do is I print this C table here, which is the lookup table, and I can show you what they look like graphically, which I think is what Andrej does as well. So let me go here to let's see, change directory. What do I have here? So if I look at well, I've got two embedding tables. This first one here is the random one that I started with, and this C1 text is the lookup table that I ended up with after 200,000 iterations. So, and I have a GNU plot program here that can plot these guys out. So let's take a look at that GNU plot program. And you can see what it does. Let me first plot, I'll first plot C. So this is the embedding table. At the very beginning, just random stuff. Okay, just random stuff. So let's take a look at what the GNU plot looks like. So if I say GNU plot, have a look. So that's what it looks like, I think. Maybe I also make it a little bit bigger. So if you look at the letters here, like for example, B, the vector for B, if you think of this as Y and this is X here, then you can say that B was at, what is that, like X is minus 3.2 or something like that, minus 3.2, and Y is minus 0.75 or something like that, minus 0.75. So all of these letters now have like a vector in the XY plane because we're only using 2 dimensions. Now, if we were using 3 dimensions, then we would have X, Y, Z, and we could plot a 3-dimensional table. But what happens if we have 5 dimensions or 10 dimensions or 100 dimensions or 1,000 dimensions? It gets to be to a point where you can no longer imagine what it looks like. But anyway, all of our letters here are just randomly put here, like in no particular order. Like A is here, B is over here, J is up here, is that I is here, Z is over here, L is here, P, T, H. Okay, so they just seem to be kind of haphazard. But if we look at the table after 200,000 iterations, what does our lookup table look like? Well, it looks like this. Now, what you'll notice is like A here is here, and then E is here, I is up here, O here, U, Y. You see, for some reason, the vowels have sort of separated themselves out from the group of consonants, more or less. Now, the funny thing is that when Andrej ran his code, and he showed much nicer graphs than mine, his showed that the vowels seemed to be gathered in one spot, and the consonants were all spread out all over the place. And I'm getting kind of the opposite. But I think the important thing here is that there's definitely a pattern. And the pattern is that the vowels seem to be kind of special because they're all kind of on the outskirts. They're on the outside, whereas the consonants seem to be kind of grouped together on the inside somehow. I don't know. Are we getting into philosophy here? I don't know. Anyway, let's move on. So what we have is we have this thing. Let's take a look at. Let me run the Python code first. I think that's 4B. Do it 4B. I think this is the Python code that runs. And let's see. You notice the number of parameters is 3481. Well, how do we get 3481? Well, if you get the 5 parameters, the size of all those 5 parameters, where do I have them here? If I have a new, well, I don't need this one here. If I go to, can I go to a calculator? Where do I have a calculator? Calculator. Let me bring up a calculator while we're waiting for this. If I go and say, okay, weight, or let's see, B1 is 100. So if I take 100 and I add that to, I add B1 to, that's B1, and B2 is 27. So that's B1 and B2. Now W1, where's W1? W1 is going to be 600, I believe, total. These are just the size of these tables. And W2, where's W2 is going to be out nodes is going to be 27 times hid nodes, which is 100, 2,700. I think is that 2,700. And C, our lookup table, is going to be 27 by 2. 27 by 2 is 54. So that gives us, I hope, 3481. And you can see here 3481 is the number of parameters, which is basically the accumulated size of all 5 of our tables that we're looking for gradients. So we run this I don't know how many times, and we started off with a loss of 4.02, and then we go down to 2.15, and then the final loss of our training set is 2.067 or 2.15 when we just run the training set by itself, and our development set is 2.4, and those are the names that we produced here. Those are the names we produced. Now, if I was to run my C program, of course my C program will take a long time. Let me just go to a new window here. Is my C program going to print anything out? Yeah, I think my C program, where do I have it here? Yeah, let me just comment out this. I want to just comment out this printing of the. Well, actually, you know what? I can leave that in there. Yeah, it's fine. Let me just compile. WALL. What did I call it? P7B minus LM minus LGSL, and I'll also add in a touch of optimization just to give it a little more speed. But why do I keep getting it wrong? Sorry. So I compile that, and I can then run it. Now that's our lookup table before we started, and I put it in a form that GNU Plot understands. So this is our random lookup table before we did the all the iteration and all the optimization and all that. But you notice my parameters here, 3481, same as the Python program. And in fact, if you look at the numbers we're getting, 4.022905, which is same, 1.9572, 1.9572, 2.315, 2.315. So my numbers are what happened here? Is it over? Oh. Well, there you go. It's mine's over, and this one is over. So you can see that the losses here from the Python program was 2.41, and mine was 2.4175, which is same as that, and 2.1577, 2.1577. And you notice the output here that I got, the names I got were the same as the names produced by the Python program. Okay. All right. So let's close this for now, and let's take a look a little bit at the code here. So I have the code here, and I also want to show you the formulas. Here are the formulas that I used for the backpropagation. So if you look at, first of all, we get the we get the embedding table. And I showed you how in C, how we can use the X and the lookup table to produce the embedding table. Once we have the embedding table, we can get H, which is our hidden layer of 100 neurons. We can multiply our embedding table by W1 plus add the bias 1. And that gives us our hidden layer. And then we activate the hidden layer by taking tan H of that. And then we get our result, which is our predicted values, which are Z times W2 plus B2. So our forward pass is very straightforward to generate. And we can look at here the forward pass we have here is right here. See, we get a mini batch, okay, from the training set, which is 32 basically, 32 bigrams. We embed them to get our embedding table, and then we generate H by multiplying it by W1, and then we add the BIOS, which is what we did up here, and then we activate with tan H. That's this line here. We get our logits by multiplying H by W2 or Z by W2. So I'm not really using Z here, I'm just using one array H all the way through. And we add bias to the logits, and then we get cross entropy, we get our loss. So that's our forward pass right here, which is identical basically to what they're doing in the Python program. And then we go into backpropagation. Well, backpropagation is a lot more complicated in C, because what I need to do is I need to get the probabilities using softmax. And the first thing I do is I get dl dy. This is dl dy. And I can just do this summation here. So if I look at the code, this is all, I have everything posted on GitHub, so you can just download everything and have a look at the code at your own leisure. But if I look at get dl dyp, I don't know where the heck that is. Right here, compute the gradient loss with respect to predicted output, update probabilities to derivatives, and this is how I do it. So it's basically just summation, and then do for each one I'm just subtracting 1. See, the actuals should be a 1. That's the I think they call that the class that I'm looking for is a 1, and all the rest of the numbers should be a 0, but obviously they're not going to be 0. And then I have to do dl db2, and you can see here's the function here, get the db2, get b2 grads. That's this function here. So it does dl dy times dy predicted by db2, and you see how they chain rule just cancels that out. And then I got to get the loss with respect to w2 right here, the loss with respect to w2, and in order to do the multiplication I have to transpose h. It's one thing you got to worry about when you're doing this yourself, is you got to make sure that all of your matrix arithmetic will work. And the beauty of the PyTorch is that somehow it just figures it all out. I think only God knows how that works. I don't. So this is dl dw2 right here, and then we have to get dl db1. Well, in order to get dl db1, you notice we need dy dz and dz dh. So I think I have here get dh dz. I don't know if I have, or do I have that backwards? I can't remember. Well, where is dl db1? Right here. So in order to get these guys, See, I need to get DL, DL, DZ. DL, DZ is just going to be, I think, these two here. It's been a while since I wrote this, but they do work, believe me. You can see I did get exactly the same numbers that we generated from the Python program. So I know they work. And then you get the W1 grads. Then we get the C grads. Well, the C, this is just basically unembedding. As I showed you before, unembedding. And then we do an update. And the update involves the learning rate. Okay. And then we have MakeMore function. We go through all of this just like we were doing with the Python program. We embed. Basically, we're just taking, notice here we have a number of bigrams is 1. We're just starting off with 3 zeros, and we embed into those 3 zeros into C, and we get the embedding matrix. We multiply that by W1 to give us H. We multiply, or we add in bias. We activate our neurons, and then we get our logits, our log counts, by multiplying H by W2 and then adding the bias 2. We get the probabilities by the softmax function, and again, this line I had to do kind of a kludge. I had to change these probabilities, which were floats. I had to change them into doubles, and the reason I need them into doubles is because this multinomial function out of the GNU scientific library requires doubles here. And then what I do is I select one random number out of this probability distribution, and I print those letters out one at a time, and I update my X, and I just go around and I get count. I do that count. I get 20 characters, or 20 names, 20 new names printed out. And you can see the names I printed out were the same as the other ones, as the Python ones. All right, what else is there in this part of the code? Well, the last thing is that I've changed the code to use, instead of using 2 dimensions, I'm using 10 dimensions. So if you look at the code I have here, let's see, save, I don't want to save this. If I go to here, if I look at, I think I have, that was 4B, 4A, do it 4A. This is the one that has 10 dimensions. This is the Python program, but instead of 2 dimensions, we have 10 dimensions. So let's take a look at that code for that. 4A, I think that's, oops, display. So here is the code for 10 dimensions. It's almost identical to the one that I had for 2 dimensions. If I go down here, the only difference is that the block size here is 3, and the dimensions are kind of hard coded. Like this 30 should be 3 times 10, which is block size times dimensions. And this should be 3 times 10, block size times dimensions. So it's kind of hard coded in this one. But I still have a mini batch of 32. And I just keep grabbing random ones out of there. So in this example here, Do I print out anything here that's crazy? I don't think so. So this one is 10 dimensions. Oh, and also, instead of being 100 neurons for the hidden layer, it's 200 neurons. So I've doubled the number of neurons in the hidden layer and the BIOS, and I've changed it, and I've made it to 10 dimensions instead of 2. And this is what I think Andrej is using in his code. He's using 200 neurons and 10 dimensions. So let's see how this guy works here. If I go do it for A, then you should see the number of parameters now is 1,100 or 11,897, because that is basically the sum of all of the parameters here. So it's like 200 plus 3,000 plus 5,400 plus 27 plus 2,700. I guess if you add up all these guys, you should end up with 1189, I think. And obviously this one is slower, but you can actually see the thing running with, I think I showed this before, when I'm using, where is it here? By using a software monitor, I can monitor and see how it's working. But anyway, this is the result of using the Python program. And you can see that the losses we get now are, much better than we had in the very, very first video, which was 2.45. We're down now to about 2 or 2.3, which is still better. And our names come out to be not too bad, like Maya or Finn, Kalyan Shah, see, June, I don't know, this name here, Brooks Shamley, I don't know, maybe, or Kaileya, June, yeah. So some of the names they're not too bad names. Tori, I'm surprised that might be in the original list. I don't know. The one thing is, if you train too hard on your data set, and that's all you're using is just your one data set, then your network could be so good that it just the new names it gives are names that are in the training set, and you really don't want that. You want names that are not in the training set. Let me go and new window here, and let me compile. Which one am I doing now? I'm doing is it P7A, I think. MLGSL minus O. I think this is the one. Let me just take a look if that's actually the one I want. 7A. This is 7A. Now, do I print out any nonsense here anywhere? But you can see this one, I am using 200 neurons instead of 100. And I'm also making my dimensions to be 10 instead of 2. And my block size is 3 this time. And so again, I go through the whole thing the same as I did before. So let me compile that guy. I think I already compiled it. Leave that out. And what we can see is, you see the number of parameters 11,897, which was the same as the parameters we got with the Python script. And you notice the loss here, the very first loss I get, 4.19414, 4.194136, so it's close. Okay, so it is, but if you go to here, you can see my system is using up about, well, including the operating system, it's about 8 gigs of RAM. Seems to be, well, it's growing there a little bit, but it should probably bounce back. I don't know if it's going to bounce back to 8 or not, or is it going to stay at 8.1? Maybe I forgot one free somewhere. I can see, but you can see it's only using one CPU at a time. It's bouncing around from one CPU to another, but and I can definitely see that my memory is increasing slightly, 8.2. So it's probably somewhere, it could be I forgot to do a free on the allocated. Yeah, it's 8.3 now. Yeah, I'll have to check that out later. But I just want us to wait. It's going to take a while here because I have to go through, I don't know how many, 20 of these printouts of these losses before I can see if my answers are the same as the answers of the Python program. Now, is there anything else I can look at while we're waiting for this neural network, formulas, gradients, embed? No, I think I covered everything here. I think I covered everything. Yeah. We could take a look quickly at that. Well, I've been watching some videos lately on why they use what's that function here they use for the loss, the cross entropy. You know, if you look at cross entropy for the loss, where do I have that here? Don't tell me this one's finished already. Is this one finished? No. Okay. Oh, are the names the same? Yeah, you can see the name, the output is the same. Yeah. So my C program is producing the identical results to the and even my losses here, 2.3328 compared to 2.33279. Okay, and all of the losses here are the same as well. So everything is working correctly. So far, so good. Okay, let me close this guy up. Close this guy up, and let's see. And again, you can go to my GitHub page. You can see all the code there. Well, actually, I've been on this video for quite a long time, so I think I'm probably done. Let me close this stuff here. Close this, and close a few other things. So, all right. So I think we're done. I think the next video is going to be a really major challenge, because the next video we're going to be doing batch normalization. And the batch normalization calculus is a nightmare, especially for someone like me who barely knows any calculus. So I hope you'll join me for the next video on batch normalization, and we'll see you then. Take care and keep programming.